We're going to continue talking about acids and bases today. Again, we left off last time with buffers. We're going to talk a little bit about indicators today and integrate them into titration. We'll talk about simple titration today, and then we'll get into the more complex one next time. But again, everything in Big Idea 6, and Big Idea 6 really spreads over the equilibrium, acid base, and the solubility equilibria chapter. I would say today, tomorrow is as tough as it's going to get. And then it's downhill from there. All right, last time we finished off with buffers. Today we're going to introduce acid-base indicators, and I have a few old AP questions I'd like to take a look at in these topics, both from buffers the other day and from indicators today. With your acid-base indicators, an indicator is a substance that is a weak acid, and as a weak acid it has a specific or certain color. Indicators are similar in that they're weak acids, but they do have different colors. So as a weak acid it has one color, and if it is in its conjugate base form, it's going to have a different color. And the colors can be yellow, red, orange. They can be colorless, and we'll go through a few different indicators. For example, one is phenol red. And phenol red in its weak acid form is yellow in color. In the conjugate base form, it's red in color. If you have an acidic solution, you'll find that the concentration of hydronium ion is high. With a high hydronium ion concentration, as we talked about in the equilibrium chapter, equilibrium will shift in the reverse direction to use the hydronium ion that is present. With the shift in the reverse direction, you're going to generate that indicator as a weak acid. Ion for indicator, the H in front indicates the weak acid format of it, and the solution will turn yellow. In contrast, if you have a basic solution, let's say you have hydroxide ion will react with the hydronium ion to generate water. Equilibrium will shift in the forward direction. You'll have the conjugate base form present, and the solution will be red.
And the ion just stands for indicator?
Yep. So in this case, your indicator is phenol red, and again, ion just short for indicator. In a neutral solution, the concentration of the weak acid, that is the indicator in its weak acid form, and its conjugate base form would be the same. Red and yellow make orange, and that's what you would see there. Now, it says here, and this is not in your notes, scribble or type it in. If pH is greater than pKa, you're going to get a forward equilibrium shift. And let's think about this now. Rather than memorize, let's try and understand the concept so that if you are asked about this, you can answer it even if you haven't memorized all the pieces. So first up, we have the indicator in its weak acid form. I'm just rewriting this equation so we can analyze it. Here's the conjugate base. I wrote it backward from what's there. Let me write it exactly the same, just so it's not a source of confusion. Doesn't matter what you write first, though. So here's your weak acid. Here's the conjugate base. If we were asked to write the Ka, we could do so very easily. You've already been assessed on this. You have mastery of it, or most of you do. Some of you are a little sloppy with the charges, and you lost the point on that. Be very careful. Make sure your equation is balanced for charge, neutral on the left, one positive, one negative, neutral on the right. Make sure on top you've got those charges, otherwise you're not going to get credit. Now Henderson Hasselbalch equation says that pH is equal to pKa plus the log of the conjugate, in this case conjugate base, over the weak acid. It says if pH is greater than pKa, equilibrium is going to shift in the forward direction. And let's examine this. If pH, let's say, is 5 and pKa is 3, equilibrium shifts in the forward direction. When equilibrium shifts in the forward direction, what happens to the concentration of conjugate base indicator? It will increase. And this will decrease with a forward shift. So now you'll increase this amount, getting them closer to equal. So it makes sense that if the pH is greater than the pKa, equilibrium shifts in the forward direction, the conjugate base will be generated, the weak acid will be utilized, this quantity will increase, and as a result, you'll draw more even, which is what Le Chatelier's principle states. In contrast, then, if pH is less than pKa, equilibrium will shift in the reverse direction, because now what's going to happen with a reverse shift, you'll see an increase here, a decrease here. With a decrease and an increase, this amount will decrease, getting to the negative range, and as a result, you'll get the pH then approaching the pKa. So if you can remember this piece at least, or if you can interpret it, you'll be good to go there. And one indicator is phenol red. There are a whole bunch of indicators. If you've titrated before, you've probably titrated with the indicator phenolphthalein. There's bromothymol blue. There's a whole bunch of indicators, and the indicator you select is based on its pH range, where the indicator undergoes the change in color, and we'll talk about that in a little bit.
pH paper an indicator?
pH paper is an indicator, and it will give you an approximate pH. A better way to determine pH is to use an indicator as well as a pH meter, and that's what we'll be doing in the lab on Thursday. Very cool titration lab. You'll enjoy it. So other indicators include litmus paper, which you may have used in middle school. Litmus paper in acids is red, and in bases it turns blue. Phenolphthalein is another indicator. This is colorless in acids and pink in bases, and you can see it right here. You've got the conjugate base right here, hence the deep or the fuchsia color. Here's the acid form right here, and it is colorless. And phenolphthalein is one that is commonly used. It has a very large range. Methyl orange is another indicator. It's yellow in basic solutions. It's red in acidic solutions. And there's a whole bunch of useful indicators. Shown here are the pH ranges. I don't think I can make it bigger, but we can take a look at it. Go ahead.
Would we ever have to predict a color change based on an indicator?
You could. More likely, it may give you a bunch of indicators with their pH ranges, and once you determine the pH at the equivalence point, you'll select the indicator, and that's more of what you might see. And that is exactly what you'll see in the pre-lab that you need to do before you do the lab, because otherwise you won't know which indicator to select for your titration. And we'll work on that tomorrow.
So, do we have to memorize, like for your test or the AP exam, do we have to memorize what changes what color?
No. I don't think I could think of a bigger waste of time, except maybe all the texting you guys do on your phones.
So how is the pre-lab?
hang on. Well, we're doing the lab on Thursday. So I think we're gonna have time tomorrow. So we'll do it in class. It'll make you happy. All right. For example, here's bromphenol blue. Here's its pH range. Sometimes it's listed as a pKa range. So from about 3 to 4.5. So if the equivalence point is achieved, let's say at a pH of 4, this would be an excellent choice for an indicator. Methyl red, and let me go back here. So bromphenol blue, it goes from yellow to blue. So at the equivalence point here, you're looking for a greenish color, and you typically see the primary making the secondary color. Methyl red is red, orange, and then yellow. So if the pH at the equivalence point, which will make more sense in a little bit, is let's say about 5.2, that would be a good choice. Bromphenol blue is another one. This goes from yellow to blue. So if you had a pH at the equivalence point of 7, that would be an excellent choice. And you will see in a little bit that if you titrate a strong acid with a strong base, the pH at the equivalence point will always be 7. So that's an excellent choice. Phenolphthalein here is listed at a range of about 8 to 10, and again clear. And then this fuchsia color, it's not really shown that clearly here. And then also take a look here. A couple of them have 2 useful pH ranges. Why might that be? What type of acid do you think you have there? Not monoprotic, but diprotic. So when you see multiples, you've got a polyprotic acid as your indicator, and that can be useful as well. We'll take a look at some of those titration curves a little later on. But that's more likely the question you'll be asked. It'll say the pH at the equivalence point is 8.0. Which indicator might you select and why? So, well, what did it say? 8? Yeah, this one maybe?
What's the name?
I can't make out the first part unless it's an alpha. It's nitrophenol. I can't make it out. I even have my glasses on. I can't make it out. I don't know what that says. Do you?
No.
I'll look in your book. It'll be clear. It doesn't really matter.
Wait, so why did you pick that one over phenol red?
Phenol red, you're really getting close there. You might miss it if your titration is off a little bit. This one's more in the range. And what you're indicating here is that the equivalence point of 8 falls within the useful pH range of nitrophenol such that the color change can be observed. And we'll work on that when we do the pre-lab to make sure you've got it.
And we would read the graph.
They wouldn't give you anything so extensive. They probably would give you a few choices. For example, if we were to take a look at your lab that you're going to be doing on Thursday, it's really cool. You're going to do 2 titrations. In the pre-lab, you first have to figure out the pH at the equivalence point. I'll teach you how to do that tomorrow. But you can see here, it's just something far simpler. So let's say, for example, that the pH at the equivalence point was 10. You would follow down right here, and you would pick this thymolphthalein. And that's because the color change, or you would say in this case, the equivalence point of 10 falls within the region in which a color change would be observed. Or you can say the pH of 10 falls within the pH range of 9 to 11 for thymolphthalein, and this equivalence point pH would be observed in the form of a color change from colorless to blue, or in this case it probably would be light blue because it's some sort of in-between color there. So with red and orange, the equivalence point, you would see you'd see the endpoint color then at orange. The color change is represented by an endpoint, and we'll get into the difference between endpoint and equivalence point in just a few minutes. the other thing I really want to take a look at here is in the form of an old AP question. I don't want to show you the answers right away. Oh, can't find it. Let me go this way. And that's what's shown here. And it's a sneaky little question. Keep in mind on your AP exam you have 105 minutes to do part 2, which is a very long time. It requires a lot of concentration and a good night's sleep. Your first 3 questions will be long, about 20-25 minutes each. Your last 4 questions will be short, about 8 to 10 minutes each. Looking at a short question right here, they give you this equation. They're showing you yellow to blue. So this is a different indicator than what I showed you. It says the indicator HIN is a weak acid with a pKa value of 5. It reacts with water as represented in the equation above. Consider the 2 peakers below. Each has a colorless layer of oil, which is nonpolar covalent, and a layer of aqueous buffer dissolved in water. In beaker X, the pH of the buffer is 3, and in beaker Y, the pH of the buffer is 7. A small amount of indicator in its acidified form is placed in both beakers. So you dump HIN in here and here. Stir it up and let it settle. What is the predominant form of the indicator? That is it this or this in the aqueous buffer in beaker Y? Why? Explain your reasoning. That's not a choice.
The ion.
Yes.
The.
Be careful.
Do you have to say ion negative?
Yes. So why would it be that one?
Because the pH is greater, so it goes in the forward reaction.
And be careful with it goes in. So pH is greater than pKa.
Favors the forward reaction.
Equilibrium shifts in the forward direction. If equilibrium shifts in the forward direction, the conjugate base, ion minus, is the predominant species, and that's enough. You can say ion minus is the predominant species because pH is greater than pKa and equilibrium shifts in the forward direction, generating it. The end. No book. B. And B is one of these great questions because it's not only a question about indicators, which falls in the acid-base question, it's also a question about IMFs, or interparticle forces, and they dropped a major hint there. In beaker X, the oil layer is yellow, whereas in beaker Y, it's colorless. Explain these observations in terms of both acid-base equilibria and interparticle forces. In this case, pH is less than pKa. The reverse reaction is favored. HIN, a yellow species, turns the oil layer yellow. Why? Both species have what type of IMF? Only LDF. So LDFs form between the oil and the weak acid. In beaker Y, the oil is colorless because where is ion minus? In the oil layer or in the aqueous region? The aqueous region, because what type of interparticle force forms between the ion and the aqueous buffer? Ion dipole force. And that's all you need. All right? So it looks very, very challenging, but if you work through it carefully and you keep in mind when pH is greater than pKa, the forward reaction is favored, you'll have that conjugate base form of the indicator and be successful there.
In beaker X, why is there no reaction between the buffer and the aqueous solution in the aqueous product? why is it only between oil and there's nothing with the buffer? Because
There's very little conjugate base present because the reverse reaction is favored, so there's far more weak acid than there is conjugate base. And they only spoke about the oil layer being yellow. That's not to say there's no blue in the bottom.
okay, I get it.
Because you might have some present. All right, so those are your indicators. And with that question, makes us think, okay, we really need to understand that concept in regard to if pH is greater than pK, the forward reaction is favored. We're going to talk more about selecting appropriate indicators when we do our equilibrium component. Not our equilibrium component, when we talk about the equivalence point in the next section. The other piece we want to introduce today, but we're going to dig in more deeply tomorrow, are neutralization reactions and titration curves. Now, years ago, you only needed to be able to do the math, and that was it. Now you need to be able to generate a curve, analyze a curve, and your lab is going to help you greatly with that because you will be measuring the pH as you add 1 ml of either strong acid or strong base to whatever it is you are titrating. You will generate a curve using an Excel program. If one of you wants to switch it over to Google Sheets, that would be great. Let's take a look at neutralization and titration curves. Neutralization, very simply, is the reaction of an acid and a base. We're going to look at 3 different ways to do it. We're going to do strong acid, strong base, which is the easiest. Very unlikely to be asked about that. Weak acid, strong base. Weak base, strong acid. And we'll march through the first piece today, and I just want to start to introduce some similarities and differences. Titration is a technique that you use to neutralize an acid or a base using the other, and it is a way for you to determine the concentration of a substance at different stages of the titration. It's also a way for you to determine the equivalence point. So you can determine pH every step along the way. You can determine concentration, volume, etc. There's a lot of different things you can do with it, but it's more analytical in that it's quantitative in most areas. You can get qualitative if you're seeing color changes, etc. The equivalence point is the point at which you mix acid and base together in stoichiometric proportions. The equivalence point is where millimoles of acid and millimoles of base are equivalent, stoichiometrically equivalent. And in these particular problems, you typically have a 1-to-1 mole ratio, making it very easy. The end point is when the indicator changes color, and the differentiation there is critical. The end point occurs at the equivalent point, the equivalence point occurs at the end point, but the end point signifies the color change, the equivalence point signifies where millimoles of acid and base are the same. We are going to be plotting titration curves, which are graphs of pH on the Y versus the volume of the titrant. The titrant is what's in the burette. That's what you are using the stopcock to let flow out. And we can measure pH with a pH meter, which we'll also be doing in the lab on Thursday. The first type of titration we want to mention is the titration of a strong acid with a strong base. This is the easiest of the bunch. For example, this shows the titration of a strong acid, nitric acid, that's what would be in your flask or your beaker, with 0.1 molar sodium hydroxide. The sodium hydroxide is your titrant, and that is what you would have in your burette. That's what you're dispensing into the flask, and you're doing it in 1 or 5 ml increments depending on what the volume is. You're starting with an acid, you start with a low pH. It's a strong acid making its pH lower and lower. The equivalence point when you titrate a strong acid with a strong base is always 7. At the equivalence point, the pH is always 7 for a strong acid, strong base. This shows the titration or a pH curve of base with acid. So the hydrochloric acid, the strong acid now, is in the burette. The sodium hydroxide is in the Erlenmeyer flask or the beaker. How do these two graphs, how are they similar and how are they different?
Equivalence point is in the middle.
The equivalence point for both of them is 7. They both have pretty steep areas on these curves right here, shooting straight up here and here. This starts from low pH and goes to high. This one does what? The opposite. You've got almost a mirror image there. In both cases, strong acid, strong base, strong base, strong acid. pH at the equivalence point for a strong acid and a strong base is 7. What we're going to be doing in this section is we are going to determine the pH at several steps along the way. So in this particular example here, we would have a situation where we have strong acid we'd have an indicator and in our burette we'd have strong base. So this would be our titrant and this would be our analyte. And if your indicator was phenolphthalein, it would be clear and acid. So in this particular example, we have hydrochloric acid, and the concentration of this acid is 0.5 molar, and the volume of the acid is 20 mils. The concentration of the base is 0.5 molar. We're going to add increasing volumes of sodium hydroxide, and we can figure out the pH every step of the way. First thing I want you to realize right off the bat, how many millimoles of acid do I have? 1/2 of 20 is 10, right? At the equivalence point, you need stoichiometrically equivalent amounts of acid and base. So how many millimoles of sodium hydroxide do I need at the equivalence point?
10.
You need the same, 10. What volume of titrant must I add at the equivalence point?
20 mils
Why?
to make it 10 millimoles.
Exactly. So if they have the same concentration, they'll have the same volume at the equivalence point. If not, you could figure it out very simply. to get the volume, then keep in mind here concentration is equal to millimoles over the volume in mils. So if you have the concentration and you have this, just interchange these two. Millimoles over concentration will give you the volume. So just a couple things I want you to see. And also the math here, 1/2 of 20 is 10. Keep it simple. Don't go 20 times 0.5. Move the decimal. Come on. Quick. You can do it. The other thing I want to mention is if you have a strong acid, strong base, in every instance, remember you're only interested in the proton or hydronium ion there and the hydroxide ion here, and this will go to completion to generate water. So with a strong acid, strong base, your net ionic equation will be this, or if you want, you can do this. Just make sure the equation is balanced, and some of you did not do that on your mini quiz. Be careful. All right, so we are going to add, let's say, 5 mils, 10 mils, 20 mils, 25 mils, 50 mils, whatever, of this to this, and we want to determine the pH every step of the way. This first example is all written out. I'll highlight the key points, and when we do the weak acid with the strong base, we will do every single piece of it because it's so much fun. All right, so I already showed you the relevant equation. First question, and again, refer back. Calculate the pH at the following points. In the titration, the 10 millimoles of acid doesn't change. The concentration of base doesn't change. What you're changing here is the volume of sodium hydroxide you add. Initially, you haven't added any sodium hydroxide. You just want to know the pH. You have a strong acid, no rice necessary. We know from last year that if you have a strong acid, it ionizes completely and pH is equal to negative log of the concentration. Concentration of the acid given at 0.5, that is the concentration of proton. Your initial pH is about 0.3. And again, given to you in 3 sig figs after the decimal. That's not something new. Here's where we get into the fun stuff. After the addition of 10 mils of 0.5 molar sodium hydroxide, that's the half neutralization point. How do I know that? You knew you needed to use 20 mils to get to the equivalence point, so half of that. Be careful with that. The other way to go about it is that when you have added this, half of 10 is 5. So you've neutralized half of the acid because you started with 10 millimoles. If you add 5 millimoles of the base, you'll have 5 millimoles of the acid left. So this is half neutralization point. Half of it is neutralized. So again, the millimoles of the acid doesn't change. That's why I pointed that out initially. You've added 5 millimoles of sodium hydroxide, which is the same thing as 5 millimoles of hydroxide ion. It's a strong group 1 base. Shown here is your Ryocan table. Here's your net ionic equation. This didn't change. You added 5. You take 5 away from both. You don't need to add it to the right. How come? Water is a liquid. You have 5 millimoles of strong base left. To get the pH, I need the concentration of this. I have 5 millimoles. I had 10 mils of base and 20 mils of acid for a total of 30 mils. 5 over 30 is a sixth. Concentration, pH is negative log of. So the pH really didn't go up very much, very little in fact. Now, we add 20 mils of 0.5. That's 10 millimoles of base, and we know we are at the equivalence point. And at the equivalence point, what is always the pH if you have a strong acid titrated with a strong base? 7. So nothing doing there. Now we can go just past the equivalence point. We've got 20.20 mils of 0.5. That's 10.1 millimoles of base. And some of you asked me about this the other day. I said, be careful. You can't take away more than what you have. Look right here. Where did this 10 millimoles of acid come from? It's what we've had all along. It was 20 times a half is 10. We add this, but you can't take away more than what you have. So you only take away 10, and now the only thing you have left is base. Can you get the pH off of the concentration of hydroxide ion? Sure. What's the total volume you have now? You had 20 mils of acid and 20.20 mils of base. So you have 40.20. Divide the two. Here's your concentration. Negative log of 14 minus to get the pH. So in regard to a titration of a strong acid and a strong base, we illustrated that the pH is very low at the beginning of the titration. The pH changes slowly until just before the equivalence point. Just before the equivalence point, the pH is going to rise sharply. Let's take a look at that. So right here, low, and it's a very slow rise. Even at the half neutralization point, it hasn't increased that much. Now, when you get close to the equivalence point, you get this steep up. Equivalence point of a strong acid with a strong base is going to be 7, and then it'll continue to rise and pass the equivalence point as such. And that's what is indicated here. An indicator whose color changes in the pH range from 4 to 10 can be used. But if the pH at the equivalence point is 7, what might you select here? Probably that one, bromothiamyl blue. All right. Now, phenolphthalein you can use also. Phenolphthalein, I think, is written a little bit funky because this is clear down here and you can't see clear. So they didn't do a good job with that. It is a little bit misleading. But that's one that you very often use in honors because you typically just do a strong acid, strong base. What we're going to get into big time tomorrow is a weak acid with a strong base, but I just want to give you a few things to think about here. Here is a pH curve for the titration of 50 mils of 0.1 molar acetic acid with 0.1 molar sodium hydroxide, and you're going to be using acetic acid and sodium hydroxide in the lab. Look at this curve and tell me how it differs from the curve we saw previously. Go ahead. The equivalence point's 9, so it's greater than 7 in this one. And is it as steep? No, it's more slanted. What about the initial pH? That's a little bit higher. All right? So those are a few things to think about. Also, if you have 50 mils of 0.1 molar acetic acid, how many millimoles of acetic acid do you have? 5. So how many millimoles of base will you need at the equivalence point? 5. So if they have the same concentration, what will be the volume at the equivalence point of the strong base? 50 is correct, and this will be the half neutralization point. And what you'll see with a weak acid and a strong base is that at the half neutralization point, pH is equal to pKa, and it'll be very easy to determine. We will be going through this weak acid with strong base in excruciating detail. Tomorrow, it looks like a lot. I'm going to walk you through every single step of the way. And then we also want to analyze the graph in excruciating detail. And then you will be walking through a weak base with a strong acid. And we can do both pre-lab questions here so that you have a good understanding of this concept. The other thing I wanted you to take a look at was a buffer question from last year's AP exam. I just want to look then at one component of it, and I had highlighted it off here, and maybe we can just think about actually I think we'll take a look at this tomorrow. So what I want to make sure you understand at this point, titration is a way that you can determine concentration. You can use it, as we will, to determine pH. There are a lot of different ways you can titrate, and we'll be exploring more of that tomorrow. You also want to understand the ins and outs of indicators, and we'll be talking more about indicators tomorrow as well. We'll finish up with acid and base tomorrow. It requires a ton of practice. Make sure you're putting that practice time in to be successful.